Good morning, everybody. Thank you for joining this webinar. Today we are here with my colleagues Maria Chiara Caruso and Lucrezia Lodi from RINA Consulting. We are going to talk about the environmental and economic analysis of ZHENIT solutions. And of course, as always, if you have some questions during any point of the webinar, please feel free to write them down in the chat or in the Q&A section, and we will answer them at the end of the meeting. The meeting is being recorded and they will be available soon on our project website and on our social media channels. So stay updated there to know when it is uploaded. Okay, I think we can start with the presentation. So I'll leave the floor to Maria Chiara. Thank you.
Thank you. So welcome also from my side. As already said, Martina said, we are presenting the fifth webinar from the ZHENIT project. This webinar was organized and led by RINA Consulting, and I will discuss the first part of the presentation, then I will leave the floor to my colleague, engineer Lucrezia Lodi, for completing the presentation. The webinar is divided into three main steps, which is first of all the overview of the ZHENIT project and technologies. Then we will go through the methodologies that we usually use for the assessment of the environmental economic impacts. And then we will focus on the results for the ZHENIT solutions, looking at the life cycle assessment, life cycle costing results, looking at the technologies and on the technologies installed on board vessels. Just a quick overview of the ZHENIT project and technologies. So ZHENIT is a EU-funded project aiming at promoting the waste heat recovery in order to make the shipping sector more sustainable, accessible and clean. And during the project, there are three main technologies that have been developed, which convert the waste heat to cooling, power, and or desalination. Moreover, an additional technology is also developed, which is the thermal energy storage, in order to be integrated with the three waste heat to X solution. Here we reported some indications on the waste heat to X technologies, and also we reported the link to the previous e-learning program and the webinar that was held a few months ago, where you can find details on the technologies. The three technologies are the waste heat to cooling desalination, to tree generation, and to mechanical work. And they use the waste heat coming from the heat generated by ships at different degrees Celsius, at different temperatures. The sorption refrigerator and desalinator uses waste heat at medium temperature, so from 70 to 100 degrees Celsius to these values, whilst the organic Rankine cycle uses waste heat at higher temperature, and therefore the waste heat is converted into cooling, heating, and power using an RC and the hybrid heat pump. Then the waste heat to mechanical work. So the low-grade heat at temperature less than 100 degrees Celsius is converted into mechanical work through an isobaric expansion engine. And then we have a thermal energy storage that control the ZHENIT technologies. The scope of the webinar is first of all to discuss the approach that we use to evaluate the environmental economic performances of the ZHENIT solution along the life cycle, and then to present some results of the performances, environmental economic performances, looking at 2 out of 4 technologies, which is the isobaric expansion engine and the sorption refrigerator and desalinator, considering the life cycle stages identified within the project. And then we will look also at the performances, not only so at the technology level, but also when they are installed on board vessels. Starting from the beginning, actually, the approach that we use to understand and to quantify the environmental and economic performances of products and services is the life cycle thinking approach. So according to this approach, we can estimate the environmental sustainability, economic sustainability, and also social sustainability. And then we look at the product or service, considering its all the steps of its life cycle, and we use according to this some methodologies, which are the life cycle assessment, the life cycle costing, and in case of social sustainability, the social life cycle assessment. Looking at the life cycle assessment methodology, so this is a structured, comprehensive, internationally standardized methodology for the quantification of the environmental impacts of a process or activity, looking therefore at the stages for the production of a product or for the process related to a service. And according also to this image that we reported here, we do not look just at the greenhouse gases as for other kind of methodologies and certifications, but we look at the all other impacts, also to other impacts, environmental impacts, such as the acidification of rain, the ozone depletion, the soil pollution, the eutrophication, giving an overall information on the environmental performance of the product or service we are analyzing. The LCA is regulated by mainly 2 standards, ISO standards, which are the 14040 and the 14044, which provides principle framework and also more specific information and guidelines to for each step identified in the methodology. Here, just to give an information on the stages that of the life cycle of products. So we can start from analyzing the extraction of resources, then the processing, the manufacturing, distribution, use, and also end of life. It can be closed in case we have a cradle-to-cradle analysis, as we will see soon after. When and how and why we use the life cycle assessment methodology. It is very useful for identify opportunities for improvement, the product and the process life cycle. Also as a decision support for the definition of environmental priorities in case of improving brand reputation, in case of LCA developed by producers, let's say, and also for a product development in order to, according to an hotspot analysis, identify which and where we can, how we can improve the performances, the environmental performances of the product or service, in order to implement also circular economy actions, and also to analyze the supply chain in order to also evaluate supplier and eventually have strategical solutions to improve the analysis, the performance of the product or service. According to the ISO 14040, we can consider the 3 main steps of the development of the NLCA, which is the goal and scope definition, the life cycle inventory, the life cycle impact assessment, and finally interpretation. During the first stage, the goal and scope definition, we describe the reasons and the intended use of the study. And basically we will look at the functional unit and the system boundary, which is since we will provide quantitative information of the in terms of environmental impacts, we will refer them to a unit, which is the functional unit. And then we also define the goal scope, the system boundary, so what we are including in the analysis. Once we have set this information in the goal scope, we can collect the data and collect all the inputs and outputs. This is the most resource consuming steps. And therefore we will refer all this information to the functional unit and the system boundary. All this information coming from the inventory are then converted into environmental impacts through the use of life cycle impact assessment methodologies. Basically, we use European ones developed by the JRC. And according to this, we have results that then are in the last stage interpret in order to make conclusions, recommendations, and also sometimes we can also make sensitivity analysis or uncertainty analysis in this stage. So let's go through these steps. In the first step is the goal and scope definition. As said, we will define the objective of the study, so the reason for conducting the study, the target audience, and therefore who will receive this information, and so therefore how they are communicated. The scope, and then we define the scope of application. Basically, we will define the system and the study, its function, the functional unit and the system boundary, and also other information such as the data quality, assumptions, allocation procedures, cutoffs. These ones will not be described here. We will see basically now in the goal and scope definition how what is actually the functional unit and the system boundary. Regarding the functional unit, as said, it is the unit according to which we provide the environmental impacts, so the quantitative results of the analysis, and therefore this must be quantifiable, precise, and reflect the actual performance of the product. Once we have the functional unit, we define the reference flow, which is the system-specific so the reference flows quantify the system-specific resources needed to achieve that functional unit. So, for an example, the functional unit could be of a study could be to complete the complete coverage of 1 square meter external wall for 10 years with a precise opacity, and the reference flow is the complete coverage of this square meter external wall for 10 years with this opacity with, for example, paintings. So how we reach that functional unit, how we reach that functional unit. Looking at the system boundary, here we reported the steps of the EN 15804. The life cycle stages of a product or service can be schematized in these blocks. We can have in the first step, this first stage is the production stage, which includes sub-stages that are called modules according to this standard. So we have module A1, so the raw material supply, day 2, which is the transport to manufacturing site, and day 3, the manufacture itself. Then we have the second block, which is the construction process, where we have module A4, so the transportation to installations place. Then the installation or construction in module A5. Then we have the use stage block from modules B1 to B7, including the use, maintenance, repair, replacement, and operational energy and water uses. Then we have the end-of-life stages, which are modules from C1 to C4, including the construction, transport to waste processing, and final disposal. And we can include also module D, which are reuse, recovery, recycle potential. According to this, we can have an LCA from cradle to gate, so including the production stage, so the module A1, A3, from the extraction and processing of raw materials to the manufacture of the product. We can have a gate-to-gate LCA, so just considering the manufacture of the product, or if interested, just one of the other modules of the EN 15804. We can have a cradle to grave, so from the extraction, processing of raw materials till the end of life, or we can include also the benefits, so we can have a cradle to cradle LCA. Then once we have set up the system, the system boundary and the functional unit, we can start with the data collection in the lifecycle inventory stage. We have process units, including the system boundary, and for each step, we need to collect inputs such as raw materials, ancillary materials, energy, water that are entering the process, and also products, co-products, waste, and emissions to air, water, and soil that exit the process. The inventory analysis can be, let's say, the quality of the data are higher in case we have primary data. Therefore, the collection of the data is a very important stage, and the quality of the data, as said, is higher if we have system-specific data, which are so-called primary data that are directly measured in the manufacturing plant or derived from supplier specific data sheets or EPDs that are environmental product declarations. In case we do not have access to this information, we can collect them as secondary data, which are generic data from third parties. And therefore, the source of this data can be the inventory databases, literature, estimated data calculated based on formulas obtained from literature. We also try to have as possible, as much as possible, primary data. So in order to collect this primary data, we create questionnaires that are sent to people directly involved in the steps, on the life cycle steps that are included in the analysis. Therefore, we collect this kind of information. This is taken. These images are taken for ISO 14044. So we ask to compile this information, and this information should be referred to the reference unit, to the functional unit, or therefore, or if it is not possible, to what a unit that will be then converted into functional unit. Here we have just an example of generic life cycle inventory. So we collect inputs and outputs of the process, and these input outputs can be taken or can go to technosphere or biosphere. And on the right side, we have an example of the life cycle inventory of a specific data set, because as we initially previously stated, the data can be also taken from existing life cycle databases where we have inventories. We have data sets, and within them, there is, for each data set, we will have a set of substances included and flows included in the life cycle of that product. So in this case, here we can visualize what is included in the, for example, in this case, in the production of 1 kilowatt hour of energy. Then once we have the inventory, we go on the software for modeling the process, the product, and we usually we as RINA have two kind of software for LCA, which is the LCA for Expert developed by Sfera, and SIMA Pro. Within them, we have two main databases, which is the Sfera database and the EcoInvent one. Within the software, we also have the methodologies databases, which are the databases of, let's say, that helps us in quantified starting from the inventory in quantified environmental impacts. Here on the left side, we have different impact categories, as said before. So we have land use, water use, acidification, climate change, ozone depletion. So a set of environmental impacts. And how they are calculated from the methodology, the impact assessment methodology. They can be quantified with this process. So they are classified, then characterized, normalized, and weighted. Actually, the last two steps of the impact assessment are not, let's say, mandatory. In most of cases, we just stop at the characterization stage, and therefore, what we do from the and also what the methodology does. Once we have the list of all the flows, so we have the inventory. For each of the flows and the substances contributing to a defined environmental impact, we multiply that value by a characterization factor. Therefore, for example, the unit of measure of climate change is CO2 equivalent. Of course, we will multiply the impacts, the CO2 impacts by 1, because of course we do not have any conversion. But in case of methane, we have CH4, and then we multiply by 28 to convert from CH4 to CO2 equivalent. So at the end of the classification stage, we will have all the substances with their own unit of measure. At the end of characterization, we will have all the environmental impacts with the unit of measure of that impact. We can have also the normalization and the weighted and the weighting of the impacts. So the characterized results can be divided by normalization factors to compare the magnitude of their contributions to impact categories compared to a baseline. Or we can have, after the normalization, we can weight them by weighting factors in order to have just one result for the whole life cycle of the product or service. So the unit of measure for the weighting is point. We will have just one value that, of course, will not give the information of single contribution to the steps of the life cycle and or to the environmental impact of the single environmental impacts. Finally, in the LCA, we then interpret the results. So we will have the results from the life cycle impact assessment, and in the life cycle interpretation, we can highlight the most relevant impact category, the most relevant life cycle stage, the most relevant process, and the most relevant elementary flow. According to this, there are different actors involved in the production process or in the let's say in the development of the service or whatever, and this information can be useful for one or more of them. Now, regarding instead the life cycle costing methodology, so this is also a structural method that quantify the economic impacts associated with the life cycle of a product or service. It is regulated by, again, ISO 14040, but also from by the SETAC guidelines and ISO 15686. Also in this case, the LCC is very useful for different purposes. For example, for measure of course, the main result is to measure the impact of the life cycle of product, process and system, considering both capital and operational costs. It is very useful to compare costs over the life cycle, also using different suppliers or procurement systems. It is used to define trade-off in order to identify which are the aspects that have the greatest impact on the life cycle, and also for product process development in order to quantify the most impactful contribution to understand the cost of early failures in equipment selection and use. Let's say the framework of the LCC is the same of the LCA. So we define the goal and scope, we go through the life cycle inventory, then we assess the impacts, and then we provide interpretation. Regarding the scope of application is similar to the LCA analysis, but the point of view of the analysis is different. Indeed, there are different actors that are involved in this analysis, such as suppliers, consumers, producers, and waste managers. And moreover, in this stage, it is not important to have the conversion that we said before during the life cycle impact assessment, because the indicator, the environment, the economic impacts are indicated and expressed in euros. Then in the inventory analysis, we need to collect the data for quantifying the costs related to the life cycle of the product. And therefore, we can collect operation cost, operative cost, and capital costs that are mainly the ones that are reported in the right table, and therefore we collect costs related to ancillary and raw materials, energy, transportation, packaging, also, for example, personnel, which are personal costs, including wages and working costs, operational costs related to maintenance, and so everything that is included in the life cycle stages that are defined in the system boundary. We also need to collect the CapEx cost, for example, regarding the equipment, such as investment costs related to building site, transport means, equipment, and others. Some of the costs can be cut off, for example, the office items, protective equipment, or technical support. All this data, of course, can be primary data or secondary data. Also in this case, in case of primary data, they are directly provided by the person involved in the analysis. For secondary data, they are taken from existing databases such as Eurostat, or from literature data or market reports. Once we have this information, we can through the following formula, we can quantify the cost per functional unit. Of course, once we have the cost and the quantity of raw materials, the cost and the quantity of energy, the cost and the quantity of so thermal energy and electrical energy, and also the annual production of the product, the lifetime, the investment cost, for example, for the machinery and the lifetime of the machinery. Also, if we have the man hours for producing, for the production maintenance operation, once we have all this data, we can quantify the cost of the product under analysis. Of course, this can be then let's say compare with similar products having the same function and considering the same functional unit. This information is then, these results are then interpreted in order, of course, to identify economic criticalities, for improvement scenarios, for comparison, and then also limitations are reported in the interpretation, such as also and also sensitivity analysis and let's say also the uncertainty analysis of the whole life cycle costing. Then I will leave the floor to Lucrezia. I don't know if you want to share.
I will share shortly. I think you should be able to see just in a second. Okay, I think it is working.
Yes.
So thank you, Martina, for the introduction, and Maria Chiara for the previous part. It's a pleasure to be here today. So the first thing we want to present is how we approach to the process Maria Chiara has just depicted. So we have started by defining the system boundary and the functional unit. And then through one-to-one meetings with technical provider and also by later communication via mail, we firstly shown them during the call, the LCE and the LCC questionnaire to be filled. Then after they start to collect data, we discuss about the data they have collected and refine it. And then we also review it and complete the data collection. In this slide, we are showing the kind of inventory we are referred to. So the idea was to collect the system composition in terms of main components and subcomponents, and also the materials composition of the components that was due for LCA analysis, and also the lifespan of each component were asked. And after, for LCC purposes, we also ask the cost of the components, and also for both for LCC point of view and for LCA, we ask about the maintenance and the replacement over the lifespan of the technology, because it can be that a component must be replaced before the lifespan of the whole technology. And we also ask them about the energy, the fuel and the water consumption necessary for running the technology and the main output of the technology in terms of energy or in terms of whatever the output could be. So the first technology we're going to present you is the isobaric expansion engine developed by Tecnalia. So in the right part of the slide, you can see a picture of the technology. And as a system boundary, we have defined the production module, so module between AI and A3. And the functional unit has been defined according with technical provider in 1 kilowatt of mechanical work, and the temporal scope has been defined as 15 years. The benchmark that will be also presented in a few slides has been identified as an hydraulic pump. So one thing important to highlight is that we cannot in open manner show the data about the quantities involved in the technology and also the cost involved in the technology. So the idea of this slide is just showing you how the module are splitted and which component are constituting module A1. So as Maria Chiara showed previously, module A1 is mainly constituted by the raw material supply, and you can see here the main components and subcomponents of the isobaric expansion engine. For module A2, we consider different types of transport, so truck, train, and ship, while for module A3, which is the processing and the assembly, we considered the fabrication of the components and also the assembly. Then you can see here the benchmark, which was an hydraulic pump, and we were able to collect the quantities involved. So you can see here a short representation of the quantities involved and the main components they represent. So again, for the same reason, so for the sensitive nature, we cannot publicly disclose the cost, neither from a CapEx point of view nor from an OpEx point of view. But the idea here was to show which type of cost data we have considered. So for the CapEx, we have considered the components cost, while from an operational point of view, we consider from the personal perspective, blue collar and R&D specialist, while for the utilities, the electricity required, the thermal power, and also the seawater. So here it is a first slide of results of the technology, and in the left part of the slide you are able to see that stage 1, as it was expected, is the main contributor to all the environmental impact category, and which is mainly related to the material present in the components and also the weight of the components. And after module A1, the second most impactful module is A3, while the transport are quite negligible. So just to give a more interpretation of the results, we have also considered the splitting of module A1 in various main components. So heat exchanger is the most contributor, and its contribute range between 28% from resource use mineral and metal environmental indicator to 73%. And going more in depth about the dataset we have used to model this component, we were able to see that the steel is the responsible for that environmental behavior, and also the metalworking related to that. And also other important and relevant contributor are the isobaric expander and the feed pump. And another interesting thing that emerged was that the ozone depletion is mainly due to refrigerant, as already known in scientific literature, and also from check valve for oil and isobaric expander. Going more in depth about that, it came out that it was tetrafluoroethylene in ceilings the main responsible for that behavior, and also the refrigerant itself. So the identification of the benchmark I previously presented was, let's say, beneficial to discuss later the results of the isobaric expansion engine compared with the benchmark. And you can see that EA in technology in ZHENIT project has a lower environmental performance, but it is important to consider that this is an early stage of development, while the benchmark is already at a commercial level. So all the optimization in terms of mass, of manufacturing quantities, and different kind of optimization already occurred for the commercial level benchmark, and have not already been done for the EA at ZHENIT technology level. So we discuss about it with technical provider, and they suggest us a percentage of reduction for the steel, which is the material who most contribute to the environmental performance, and it is a reasonable value. So by considering this reduction of 35% of steel, which means that the overall steel is just the 55% of the original present in the LCA of the isobaric expansion engine, you can see that the trend is the correct one, because the isobaric expansion engine in the orange bar are the same shown in the left part of the slide, while the light gray is representing the mass optimized, and yet it is yet over the benchmark, but this was just a first attempt to see how optimization could affect the results, but it considered only the steel and not all the materials involved, and also the metalworking and the material working. So you can see that just modifying the percentage of steel, the results are quite better than the previously shown. And from the life cycle cost point of view, again, since it is a prototype and it is not a commercial level, and so that is not cost competitive, the results of ZHENIT technology are worse than that of the benchmark. But the most important information results from that is that material and the purchase part are the primary cost driver, and they correspond to the majority of the cost split, and it is followed by the processing and the personnel, while the utilities cost is quite negligible. Then we will move to the second technology we're going to discuss today, which is the sorption, refrigeration, and desalination. So the goal was again evaluate the environmental and economic behavior, so the benefits and the burden that might be related to the production of technology. And system boundary was again only related to the production, so module A1 to A3. The functional unit was defined in accordance with technological developer as 1 kilowatt of cooling, and it is corresponding to 0.0015 meter cube of desalinated water, and it was evaluated of the enthalpy of vaporization. The lifespan of this technology is 20 years, and the benchmark, since the function of SRND is doable, also the benchmark must account for both the functionality. So the cooling function is described through a heat pump, while the desalination unit has been modeled through seawater reverse osmosis technology with a conventional pretreatment. For the same reason of before, we cannot show the quantities, the dataset, or the amounts current present in the inventory of the LCA, but the idea is again to show how it has been splitted. So for module A1, we account for hydraulic pump, vacuum vessel, and vacuum tank, the electrical cabinet, piping connection, and valves. The transport was split between 3 options, so truck, train, and ship, and the mechanical processing account for mechanical cutting, welding, and assembly and commissioning. So this module splitting considered the functionality overall of sorption, refrigeration, plus desalination. While for the benchmark, as already presented before, we consider both the functionality. So the cooling function was represented through a heat pump, and the heat pump available in the databases is a 30 kilowatt heat pump, and we scale it through a cup of geothermal pump assumed equal to 4, and the 4 corresponding to a 22 kilowatt of chiller. And so this is the reason for which we have divided the dataset for a factor equal to 20. While the desalination function is modeled through a seawater reverse osmosis technology with a conventional pretreatment. But since the dataset available on the databases refer to drinking water production, but our functionality in the project is not producing drinking water, we considered first the dataset representing this project, but we depleted the quantities related to the production stages that we are not interested in considering. So since after reverse osmosis for the dataset there were carbon dioxide treatment, lime, and also sodium hydrogen sulfide, which represent steps after the step we want to consider for our benchmark, we simply sum in a negative way this quantity in order to have the benchmark as similar as possible in terms of functionality to our ZHENIT technology. And again, for the same reason, we cannot show the cost of the technology, but again, we consider for CAPEX the components, and for the OPEX, the blue collar, the specialist, and as utilities, the electrical power, thermal power, and seawater. So the first results, as for the EA, suggest that module 1 is the major contributor, and its minimum contribution stands for 75% for ionizing radiation, which is related to human health indicator. And again, we want to go more in depth and understand which are the components that most contribute to this behavior. And it has emerged that the vacuum vessel is the most impactful, and it accounts at least for 55% until 70% of the total impact. And that is already, again, due to the steel that constitute the components and its working. And also, we have to consider the fact that some components are much more heavier than others, and so this also may be the reason. And the electrical cabinet is the second most relevant contributor, in particular for the indicator corresponding to ecotoxicity and resource use. And again, here you can see the comparison between the SR&D ZHENIT technology with the benchmark. And as already said, this is the environmental performance of the SR&D technology is worse compared to the benchmark, with then the exception of the ozone depletion that you are able to see here. So in particular, the environmental impact of the benchmark technology corresponded to 64% of the environmental impact, and the ozone depletion account for 4% of the impact generated by the benchmark technology, and that is due to the refrigerant used in the heat pump. And also from an economic point of view, since SR&D in ZHENIT project is not at a commercial level, it's just a prototype, so all the optimization in terms of mass of manufacturing has not really been done. You can see that while ZHENIT technology represents 100%, the SR&D is representing an average of 30%. And that is due to the fact that are different development stages that are compared here. Then if you want to, in order to go more in depth about the splitting, the majority of the cost is related again to material and purchase part, while the mechanical processing personnel are secondary, and again the cost of utilities are negligible. And after we have concluded the vertical analysis, so just considering the technology as itself, the idea is to consider the impacts of the ZHENIT solution integrated on board of the vessel. And we start from, again, the inventory, but in this case, the inventory is just not the production of the technology, but we have also to consider the installation on board, both from a transport point of view and from the production, the additional material that are required to install on board on the vessel, the technology. And the use phase accounts for the replacement, because we have assumed that the vessel lifetime is 25 years, and maybe the technology could be 15 years or 20 years, as already shown for EA and for SR&D. So we have to consider the replacement of the components, while the operational energy use is represented by the fuel consumption, because one part of the analysis was concerning the LCA inventory, while the other part was related to the fuel consumption. So we consider the baseline of the vessel without the ZHENIT solution on board, and we consider so the fuel type used, the fuel consumption, and then we supposed to include the ZHENIT solution on board, and we estimated the fuel saving related to that installation. And so to model the fuel, we consider a data set for the part of the production of the fuel, while for the combustion part of the usage of the fuel, we consider the emission factor derived from fuel maritime directive. So this is just an idea, because the results are not definitive, because this is just one of the 3 vessels involved within the ZHENIT project. So data shown here might change, because it's an ongoing activity that will end by end of March, April, and its intent was just to show how we will approach the analysis. And also fishery vessel is the smaller vessel between the 3 considered, and it is a fishery, while other 2 vessels are a cargo and a cruise, so also their fuel consumption are different. But the idea is to show that the installation of, for example, isobaric expansion engine on board of the fishery results in average reduction of 0.4 in the impact for 12/16 indicator, while there was an increase of 2.6 for 4 indicator. And it is important to say that the most impactful factor between the all considered is the fuel consumption over the 25-year, and it represents the most relevant contributor, even if compared with technology production and maintenance. So again, with the same logic, so these are not definitive. The results could change because the analyses are ongoing, and this is just for the time constraint, an example on fishery, but we are not going to show neither the cruise nor the cargo. And again, the sorption refrigeration installation on board results in a reduction, an average reduction of 1%, while the increase only for indicator was on 12%. And again, as I've said for the EA, the most relevant contribution stems from the fuel consumption, and also with respect of the technology production and maintenance. So I thank you for your time, and I will leave the floor, I think, to Martina.
Thank you, Maria Chiara, and thank you, Lucrezia, for the presentations. Of course, if you have any questions, you can write them in the chat right now. I don't see any of them, so I think I can just remind everyone that the meeting has been recorded and it will be uploaded on our social media channels and on our website. So if you missed maybe the beginning of the webinar, you can watch it again there. Of course, if you have any questions, maybe in the next few days, you can contact us on our website and we will be really happy to answer you there. I don't see any questions, so I think we can close the meeting. Thank you again to Lucrezia and Maria Chiara for your presentations, and thank you everyone for attending. We will see you in the next webinar for the ZHENIT project. Thank you, everybody.
Thank you.
Bye-bye.
Thank you. Bye-bye.